Okay, well, let's get started. Today we'll hear about something it's a bit different, but I think really quite exciting. We know about topological insulators and edge states and whatnot for electrons. But it turns out that if you worry about electromagnetic waves, you can do a lot of things which are analogous or similar in some way. And Solzhenitsyn's group, by doing that correctly, at MIT has really gotten a lot of mileage out of this kind of approach. And so Yi Yang will be telling us about that today.
Yeah, thank you so much. Thanks for the introduction. So today I'm going to talk about electromagnetic scattering in both near field, far field, and synthetic. So I would say like the synthetic part is deal with topological photonics, while the near field and far field mostly deal with nanophotonics. Okay, so before I start, I would like to thank our MIT team and our external collaborators in different places around the world. So today my talk composed of three aspects. The first one focuses on far field scattering with plane waves. And second one is the near field scattering from free electrons. And third one is the synthetic scattering from magnetic flux tubes that's created in an artificial way. So first I'll talk about a far field scattering measurements that allow us to propose a nanoscale framework for electromagnetism. So we know that nanophotonics have entered a regime where you have extreme length scales. And these configurations allows you to study both science and device applications in both classical and quantum regimes. And in those situations, actually people have found that with both optics and electrical measurements, and people see there are pronounced non-classical behaviors in those geometries. And these non-classical effects causes spectral shifts and broadenings. And they also severely reduce the plasmonic enhancements in those hotspots of the nanostructures. And why this happens for extreme nanophotonics? And if you think about why this pecularity happens, that actually traces back to the pecularity of a classical electromagnetic problem, where once you specify the geometry of your structure and the material composition, so you specify the entire problem completely. Okay, so in this problem you deal with the length scale of the geometry L as well as the wavelength length scale. And if you're in the scale invariant non-retarded regime, meaning that the entire geometry is very small, you can have a scale invariant solution to the Maxwell equation, meaning that you can magnify or make it a system smaller, but your solution is the same. But even in the retarded regime, once you specify the bulk materials or the surface conductivities, you can solve every quantities of your interest. And that's the reason why the lack of the intrinsic electronic length scales in those geometries in the photonic problems causes this failure of Maxwellian electromagnetic framework. And in fact, to remedy this situation, there have been complementary theoretical approaches from top-down or bottom-up approaches. The first approach is using a phenomenological treatment such as Kreibig or Genor to fix the Maxwell equation with another master equation such as a convection diffusion equation or hydrodynamic models. And the second approach is using ab initio solutions such as TDDFT. And these two approaches, actually, they have complementary pros and cons in terms of scalability and rigor. Okay, so I would like to argue today that there's a Feynman D parameter serve as a nice solutions that can manage to tackle all the relevant non-classical corrections in electromagnetic problems for length scale larger than 1 nanometers.
Okay, that's good. When you say non-classical correction, you mean it's interacting quantum mechanically with the electron gas and the materials that you...
Yeah, what I mean is actually listed in here. They deal with the non-locality response of the materials and the spill-in, spill-out of the induced polarization, as well as the surface enabled Landau damping.
And you're going to tell us what a 5-volt band D parameter is, because I've never heard of that so far. So, just warning you. So, okay.
Yeah. So this D parameter. Yeah. So this D parameter is defined this way. Okay. You have these two terms, perpendicular and parallel terms, and this D parameter is defined on the for interface composed of the materials A and B. Okay. Yeah. I'll talk about what this parameter is right after. And it was introduced like 40 years ago. And let me explain what it is. Let's now think about a simple ionic interface where you have a metal on the left and the air on the right. Okay. If you think about the equilibrium charge density, you can calculate it from quantum mechanics that it behaves like this. It drops from a non-zero value to 0 into the air. But if you think about what classical electromagnetics do is to assume that there is a stat-sharp step function at this ionic interface. And if you apply optical excitations to this interface, you have induced polarization. And again, classical E&M assume that this induced polarization is a delta function located exactly at this ionic interface. But in reality, quantum mechanics tells us that the induced polarization is actually has a non-zero spatial extent, and it may deviate from the ionic interface. And the D parameter is exactly the centroid of this induced charge density, for example, here, away from the ionic interface. So that's the D parameter, is this distance. And actually, this D parameter is sort of analogous to the classical mechanics treatment of the center of mass. Right? If you think about a ball somewhere, you simplify this as a point. And that's exactly what this D parameter do for the induced polarization. And analogously, you can define a parallel term, which is defined the centroid of the derivative of the surface current. So this perpendicular term is given by the centroid of the induced polarization. And since these D parameters, they are the corresponds to the dipolar term of the induced polarization decomposition, they drive effective surface dipoles and surface currents that's proportional to the field discontinuity across a given interface. And if you put this extra source term in the Maxwell's equation, you can self-consistently got a equivalent boundary condition, which is given by this. Is revised from the classical boundary conditions into jump conditions that's proportional to the D parameters. And you can easily find that if you set D parameter to be 0, this revised boundary conditions reduced to the classical boundary conditions.
So where does it come from physically? Quantum mechanically, tell me about
Oh, actually, I would say that the D parameter is coming from quantum mechanical calculations. For example, it can be calculated from TDDFT. But this revision of the Maxwell's equation is given still in the classical E&M framework.
Now that I could do, but why does the electrons, when you make a surface image charge, why is it coming outside of the material itself?
Oh, it may deal with a specific. This is actually a material quantity, because the materials they're different and the crystalline structures are different. So the electron, the induced polarization, they feel it may be expelled away from the interface, or they can move inside the interface. That's a specific characteristic of the interface of the two materials.
Okay.
Yeah.
Go ahead.
Yeah. So we build a solver with COMSOL to implement this D parameters framework. And I would like to encourage you to download to use it when you have the need. So we built a experimental setup to try to probe the D parameters, actually. And it's a quintessential a gap plasmon system that has been known to support a very strong field intensity inside the gap region. And this is from a classical calculation, and this is known from the literature. But if you also do a non-classical calculation about the surface dipole density that's proportional to the D perpendicular term, you find that this surface dipole density is very pronounced near the gap region. And this is actually implies that in the experiment you may see very pronounced non-classical corrections. And that's exactly what we do. What we see is that the experimental measurements of the dipolar resonance of the structure deviates from the classical prediction for about 300 nanometers from the dark field setup that we built in our optical table. And this very pronounced spectral shift allow us to introduce the ellipsometry for bulk for the surface, which is analogous to that of the bulk. Because we know that if you want to measure some refractive index of the bulk, you can use this surface, you have to use this ellipsometry and can get the real part and imaginary part of the permittivity of a given material. But if you do, what our aim is to invent a procedure allow us to measure the D parameter, both real and imaginary part, as a function of frequency. So we would refer to it as the ellipsometry for a surface. So experimentally, what we do is to measure the D parameter of a given interface, gold and aluminum oxide. Specifically, we sweep the diameter of the nanostructure by these three values, and we sweep the gap size across from 1 to 10 nanometers in our structure. And we record the scattering cross-section for the scattering cross-sections for each of the 2D data points, and you find that there's a constant, there's a redshift of the resonant frequencies as the gap size gets smaller. And we also do exhaustive characterization of the geometry of the structure such that we're able, yes?
How do you set the gap and how do you make it so smooth that you can bring it down to like an average?
Yeah, so this thin gap spacer is fabricated by ALD.
Okay, yeah, so it's not an air gap. It's actually
It's not floating. It sits on a ALD spacer. Yeah.
How would I relate the D parameter to the change of refractive index? Because the dispersion is changing.
Oh yeah. So.
D change, refractive index change.
Yeah, that's a very good point. Because that's actually what I want to explain here is that we measure all the classical quantities in our structure to eliminate all the contributions from the classical parts. So we know that the change of the refractive index has been, the contribution has been eliminated from our analysis. And the rest of the contribution only come from the non-classical contribution, meaning that it's from the D parameters. Yeah. So we do this characterization of the geometry of the structure with both dark field SEM and TEM to confirming the gap size. And we also do ellipsometry for the bulk refractive index of the structure as well. So I have to know that in our measurement, because of the surface-enabled Lando damping, you can find that the scattering signal actually reduces significantly if you reduce from 8.6 nanometer down to around 1 nanometers, even in a cluster measurement. And that's the reason why it's, the reason for this is that the non-classical contribution significantly reduce the radiative efficiency of the structure. Although the classical predicted radiative efficiency is already very, very low. So we have to restore this to this cluster measurement. And we do inhomogeneous broadening analysis by Voigt deconvolution, and we find that this inhomogeneous broadening is less than 10%, so which is good news to our analysis. So this shows the measured D parameters. This is a measured real part and imaginary part of the complex resonant frequency, and compare with the classical predictions. And you can find that the real part of the resonant frequency, a blue shift compared to the classical one, which is consistent with previous results with noble metals such as gold and silver. But what's more interesting is that the imaginary part of the frequency actually behaves kind of funny. Because if you see the difference between the data points and the classical prediction, you find that the largest spectral broadening does not happen for the smallest gap, which is indicates the breakdown of the Krivik broadening, which states that the smaller your feature size is, the bigger the broadening happens. And we need to explain why this happens. So to explain this spectral feature, we developed this quasi-normal-mode perturbation theory for non-classical corrections, which connects the spectral information. Omega 1 is the non-classical frequency shift. Omega naught is the classical frequency, resonant frequency. And D is the D parameter of interest. Kappa is the perturbation strength that's defined by these two quantities. And actually, they have very clear physical meaning that they refers to the classical energy density difference across a given interface in different directions. So we apply this analysis to our geometry for different interfaces, such as gold air, gold aluminum oxide, and we find that the perpendicular term of the perturbation strength for gold aluminum oxide interface is predominant. So we drop the other terms in this summation and arrive at this formula, whose inversion allow us to infer D parameters out of the measured frequency shift and the perturbation strength, as well as the classical resonant frequency. So these equations allow us to directly measure the D parameters, real part and imaginary part of a given interface. And this is the key result of this experiment. What we find is that the real part of the D parameter is very dispersionless, while the imaginary part of the D parameter is very dispersive. It can start from less than 0.1 nanometers and increase up to around 0.3 nanometer for the visible wavelengths. And this strongly dispersive imaginary part of D, which is associated to the broadening of the resonance, explains why the breakdown of the Krivik broadening. This is because at the near-infrared regime, the imaginary part of the D parameter is so small that the broadening is very small. But in the visible regime, the broadening gets magnified because of the large imaginary part of D parameter, even though the gap is relatively smaller.
I'm trying to get related to some picture of what's happening in the solid. So you have your sapphire or whatever surface, and that's very polarizable with the electric fraction. And so most of the electric field is inside there. And are you talking about the polarization of the aluminum oxide and where the charge actually sits when it's polarized? Trying to figure out what's the physical, without Maxwell's equations. Could you describe the physics of what's going on?
Yeah, actually, this D parameter deal with this induced polarization at this interface. Well, if you talk about the bulk, although the non-locality is still there in the bulk material, but without the assistance of the surface, which give you a large momentum K, this effect is typically negligible in the bulk material for the optical wavelengths and longer. Yeah, but if you're in the shorter and shorter wavelengths.
Way shorter, you're talking about things that are close to the size of the atoms. So the electron waves are not so easily, it's not like they respond at the delta function that these things do.
Yeah, I would say it's not the electron wave function, it's the polarization. That's,
but it's done by electrons moving.
No, that's right, yeah.
I'm a physicist, so I'm trying to relate this to what's going on.
Yeah, I would say you can think this as a dispersion in the momentum space, in the momentum. So if you without a surface that you cannot access that large momentum to magnify this effect.
Of course, it's a small particle. Okay, we'll go ahead.
Yeah. Okay, so that's our measurement of the D parameters, and conclude this section. So in the second part of my talk, I will talk about the near field scattering analogously, but from the free electron. So in the previous parts, I talked about this far field scattering from plane waves, but you can do something similar for near field scattering from free electrons. We can also formulate this free electron interact with the photonic structures with the scattering framework, where you have an arbitrarily defined optical environment with chi is the susceptibility, and you have this material composition as well as the specific wavelengths of interest. Your electron goes by and at a separation d, and it can emit radiation, and it can cause absorption in the structure. So we frame this problem as a scattering problem by defining the external fields of the electron as a background, and we can calculate the scattering from the nanostructure as radiation. Okay. And before we go into details, let's forget about electrons for a moment. Let's think about plane waves again. Okay, so you have induced plane waves on some structure whose susceptibility chi causes induced polarization, which can re-radiate into different directions. And we can use the optical theorem to calculate the extinction, which is the imaginary part of the incident field times the induced polarization. In a different way, we can calculate the absorption cross-section, which is the imaginary part of the susceptibility times the integral of the electric field in the scatter volume. By comparing these two formulas, you can find that the extinction is actually linear in terms of induced polarization, but the absorption is quadratic to the induced polarization. But we also know that you cannot have a negative scattering, meaning that extinction must be larger than absorption. But you also know that with simple math, that a quadratic term will definitely be larger than the linear term as long as the induced polarization is large enough. So based on this contradiction, you can find that there is a maximum possible induced current in a given scattering problem. And that's the foundation for us to derive the upper limit for the spontaneous emission of free electrons. And we can apply these constraints for the scatter power of a structure from a free electron. And putting the external fields of the electron inside this integral, we can arrive at this integration of the Bessel function. Or you can do some mathematical manipulations to arrive at a cleaner expression, which is given by this formula. You can find that there is a material factor given by chi squared over imaginary chi, and you have a structure factor that depends on the velocity of the electron as well as this impact parameter, kappa rho d, where d is the separation of the electron from the structure, and kappa rho is the wave vector of the problem that's corrected by the Lorentzian contraction. So let's test how good this upper limit is with numerical simulations. We can calculate the scattering, the emission, as well as the energy loss of the electron for different photonic problems. And we find that the numerical calculation and the upper bound, they are very close. And yes?
Sorry, just slow you down. What problem you're talking about is if you have two triangles of gold. I'm just reading that.
Yes.
I'm trying to connect with, aside from the equation
yes.
we're talking about. And so you're taking two thin pieces of gold, which are quite tiny, but at 4510 nanometers.
Yeah.
And then shooting electrons.
Inside the center of this bow tie antenna, yes.
Okay.
Yeah.
And so then you're looking at some plasmonic resonance of gold.
we're calculating the emission from this problem as well as the extinction. Sorry? Yeah?
Define what problems you're talking about.
Oh, yeah. So you have this given structure and the electron excitation of it, right?
Oh.
Yeah, so you have emission into far field. So that's the quantity that we talk about is the photon emission. And this also causes absorption into the antenna, right? So taken together, this gives the energy loss of the electron.
Oh.
Yeah.
Okay.
Yeah. So we test this upper limit with different geometries and problems and find that the numerical calculation falls slightly short of the upper limit, meaning that this upper limit can be pretty tight. That's good news. And I would like to discuss the free electron spontaneous emission in a more concrete manner by using the Smith-Purcell effect, where you have a periodic structure and your electron is flying by parallel to this periodicity, and this electron induces polarization near the surface of the structure, which behaves as an antenna array that can constructive or destructively interfere into the far field. And this the radiation wavelengths as a function of the electron velocity and the periodicity of the structure is given by this simple Smith-Purcell formula, which is nothing but the momentum conservation. Okay, and we can derive something, some upper limit for this problem. This three-dimensional scattering problem following the framework and arrive at this this formula. That's emission probability per unit length. And for the rest is similar to the previous shape-independent upper limit, but this G integral as a function of electron velocity and the KD, dimensionless KD, is something that's worthwhile looking at. So let's plot this G function as a function of beta and KD. And we find there's a bright belt that's existed in the diagram of this G parameter. And the brightness of the G function actually dictates the optimum velocity to generate radiation at a given electron structure separation. So if you're in this regime, meaning that your electron is very far away from the structure, you can the conclusion is that you should get a very relativistic electrons and let them interact with the structure. But if if the separation gets smaller and smaller, you're in a regime that intermediate velocity electron is better. But if you're in the near field, actually the non-relativistic electrons is optimal. So that's an interesting finding based on this formula. And in fact, this finding is not intrinsic to the Smith-Purcell radiation. It is actually a generic consequence of the entire electromagnetic, of the entire free electron radiation problem. If you think about this shape-independent upper limit and look at its asymptotics, and you find that for the near field, it's a logarithmic relation, but for the far field, that's exponential decaying. And they are also times a prefactor beta square. So depending on the relative how fast this quadratic term versus logarithmic and exponential, you find that there's this dichotomy of the free electron favor regime in the far field and the slow electron favor regime in the near field. So that's a very universal behavior of the spontaneous emission of free electrons. So we test this upper limit with a hacked SEM setup that behaves like this. So you have an E-beam coming out of SEM, which interact with a sample that's mounted in the SEM mount. And it can cause radiation that's collected by this by the objective and send out to the optics outside the SEM chamber. So what we find in the visible measurement of the Smith-Purcell radiation with a one-dimensional grating of silicon coated with gold, we find that we record the Smith per cell radiation and calculate the upper limit associated to this experiment, and find that both the envelope of the recorded emission agree with the prediction from the upper limit, which contains a peak around 570 nanometers. And the reason to explain this peaked envelope is that at longer wavelengths, because the reduction of the electron energy, the E-beam quality reduces, which is the result of the reduced brightness of the electron gun. So that gives a reduction of the emission probability because of the increased separation. But if you can increase even you're at the maximum E-beam energy, you'll still get reduced emission probabilities, because both silicon and gold, their material response chi-square over imaginary chi reduced significantly for wavelengths smaller than 550 and beyond, which causes reduction of the emission probability as well.
So does the peak come when the electron's going at some speed past?
Yes.
And when the photon that you're emitting has a half a wavelength or something during that speed, is what determines the frequency? Trying to figure it out.
Yeah, you can think about the dispersion of the electrons, example parabolic.
Velocities.
Yeah, the dispersion, the energy dispersion. Yeah. And
More specific. I'm just trying to.
yeah, you think about, say, the initial state and the final state of the electrons, and you draw a line connecting the two states, and this transition determines what frequency of the photon is and which direction it goes. Yeah. And we do another measurement to confirm our prediction with a near-infrared measurement with a longer periodicity grating. And we find this time there's a monotonic reduction of the emission probability, again because of the reduced brightness of the electron gun, but there's no reduction for the longer, for the larger electron energy side, which is because in this frequency window, both materials, the material response is quite flat. Therefore, the material contribution is play a less important role compared to the relative line shape change of the measured spectrum. Yeah. So the last part of this free electron emission is that we find there is a peculiarity regarding this emission probability, is the divergence of the emission probability for lossless materials, meaning that imaginary part of chi is 0. And what corresponds to this mathematical peculiarity? And we find that by using a bound states in the continuum, you are able to get radiation from electrons, as well as get enhanced emission probability. In this problem, we're simulating a structure, one-dimensional structure that holds a symmetry-protected BIC at the gamma point inside the light cone. And by tuning the electron velocity, we're able to couple the electron with the photonic mode around the BIC, and you find that there is a large enhancement of the emission probability near this symmetry-protected BIC point. And to test that whether this enhancement is accordant with our theory, we fictitiously turn on the loss in the simulation and get a well-defined upper limit. Okay. And we compare the numerical simulation with this blue line versus this simulation versus this upper limit, which is this shaded area, and we find that the enhancement still falls short of this upper limit, meaning that this enhancement mechanism is accordant with our upper limit theory. So towards this direction, we're actually now making progress. First, we test that the all dielectric lossless platform does generate Smith per cell radiation. For example, in here, using a pure SOI structure, we're able to record Smith per cell radiation in the also in the telecom relevant wavelengths using a SOI one-dimensional grating. So this work has been done by Charles, my colleague, and reported this year. So we're working towards this direction also with Hao Ning in the audience. Yeah. So the last part regarding scattering is more abstract fashion, is that we now talk about scattering of the optical waves against a synthetic magnetic flux. So this deals with the synthetic gauge fields for charged neutral particles, and is fall into the category of the topological photonics. So let me introduce this AB effect first. And we know that once you have a flux tube and you put a particle, and that's draw a contour circumventing this flux, and you can measure the interference of the particles to combine the paths, and you find that once you change the magnetic fields inside this loop, you can see the fringe shift, and that's the Aharonov-Bohm effect, which later interpreted as the real space manifestation of the geometric phase. And you can, of course, put this Barry phase, this AB phase, inside a lattice. For example, is a square lattice decorated by these gauge fields, and you can get this famous Hofstadter butterflies. And this butterfly has been realized in different platforms in solid states. In here with this Moray superlattice, and it also been done in photonics, in superlatin qubits, and yada yada. And what about the non-Abelian generalization of this Aharonov-Bohm effect? Actually, this was proposed by T.T. Wu, who is a Harvard professor actually, and by Yang Zhenning, and they propose that non-Abelian AB effect can be used to can be used to detect non-Abelian gauge fields, which was also interpreted later as the non-Abelian geometry phase by Wilczek and Z. And more recently, people are getting more interested into synthetic ways to generate non-Abelian gauge fields in synthetic quantum materials such as cold atoms, and engineered systems such as optics. And our goal here is to observe the non-Abelian AB effect with optical waves. So let me explain what this non-Abelian AB effect is. And if you think about a 2-point in space, these 2 points, and you can have 2 passes form a closed loop. And you can decorate these 2 paths with a gauge potential that are no longer commutative. For example, you can use them as a Pauli matrices in the SU2 gauge fields. And what you need to do is to swap them, theta and phi, in the upper path and the bottom path. You need to swap their swap their order. And by this simple Bloch theorem argument, no, not Bloch theorem, this is a Bloch sphere analysis, you can find that depending on whether you go from the upper pass or the lower pass, you can find that the orientation of the spin or pseudo-spin actually are different if you are combining them at the final interference point. And if you think about this in the Hilbert space, I noted before that because there's a sigma y and sigma z, they rotate the pseudo-spin in different orientations, they lead to different final spins on the Bloch sphere. And the interference of these 2 final spins in red and blue color give you the AB effect, non-Abelian AB effect. I need to emphasize that it seems that based on these analyses, these gauge fields are nothing but a single cubic gate. But I think what differentiates this gauge field is that these phases, theta and phi, they break the time reversal symmetry, so they are direction dependent phase. So both of these phases are induced by a time reversal breaking manipulation. So let's examine what are the time reversals in those non-Abelian AB effects. Okay, so in the Abelian version, you have this loop operator defined by these path integrals, and you can time reverse these path integrals by reversing both the ordering as well as the gauge field, because both momentum and vector potential are odd under time reversal. And you can find that W1 and W2, the two operators both generate e to the I gamma, the Bary phase. So therefore, actually, they're readily commutative. But if you do something similar for the non-abelian AB effect, if you do this loop operator and its time reversal partner, you can find that they are no longer commutative. So that differentiates the non-abelian and abelian AB effect. So we would like to realize this non-abelian AB effect with optical systems. So what we need to do critically is to break time reversal symmetry in different ways. So we choose to break time reversal symmetry with Faraday rotation as well as dynamic modulation. So for Faraday rotation, I think it's a high school textbook manner that you can rotate your polarization non-reciprocally by applying a longitudinal magnetic field and using a magneto-optical material. In here, we choose to use terbium yttrium garnet for its large magneto-optical response at the telecom wavelengths. So for the dynamic modulation, that's a little bit tricky, where we adopt 4 lithium nanobe modulators, phi 1, 2, 3, 4, and to drive them with sawtooth modulation specified below. Let me explain why they break time reversal symmetry. Specifically, we use a polarization beam splitter at the junction here and the junction here, such that we're able to manipulate each pseudospin individually. So we attribute upward driving in phi 1 and phi 4, but downward driving in phi 2 and phi 3. Therefore, the time delay inside the different modulator, tau, give you a non-reciprocal phase phi equals omega times tau, and minus omega tau for the two pseudospin component. So if you reverse time, this gives you a minus omega times tau and plus omega times tau phase difference for the two pseudospins. So that corresponds to the sigma z term in the interference. So in the complete setup, we combine the two ends of these elements to form a Saniac interference, and we do a projection detection in the linear basis by doing this intensity projection. And the measurement of the intensity is triggered by the pulse current in our magnetic field generator, which ensures that the measurement is done for the time when the magnetic field is maximum. Okay? So based on this measurement, we can define the observable of the AB effect. So in the abelian AB effect, we can simply look at how the interference fringe shift. But in the non-abelian version, we define a ratio between the upper pseudospin and between the upward spin and downward spin. And this rho, a contrast function, is defined on the manifold S2 times T2, and is controlled by 4 parameters: alpha, beta, theta, and phi. So alpha, beta specify where you're located on the Bloch sphere, and T square decides the synthetic gauge field, how large the synthetic gauge field is. So let me explain what the features are contained in the contrast function. So in the contrast function, there are actually 2 pairs of poles and zeros. Okay, so there's a pair of the fixed pole and fixed zero that's located at the end of the equator. That's invariant against the gauge field strength. But there's a tunable poles and zero that can be tuned along the entire surface of the Bloch sphere as a function of the synthetic gauge fields. And I call this pattern the Pepsi pattern. So our goal is to measure this Pepsi pattern. So before I show you the measurement results, I would like to talk about what are the genuine non-abelian conditions in the system. Actually, the non-abelian is quite a loosely defined term, because it can be diagnosed by the commutativity of the gauge potential, or the trace of the Wilson loop, or the commutativity of arbitrary loop operators. And in fact, the Venn diagram shows that the last one is actually gives you the a genuine non-Abelian condition, because you find that the dashed lines indicates the Abelian configurations, and you find that this last term gives you the maximum Abelian version, meaning that this is the most rigorous definition. And we can compare this. We can compare the latitude of the Poisson zero versus the loop operator, commutativity of the loop operator, and we find there's a one-to-one correspondence between the genuine non-Abelian condition and an off equator zero or pole. So that's something we will want to look at. And here's what we measure. So we can find that if the system reduced to Abelian, for example, when theta and phi are chosen to be these values, we find that the poles and zeros, they all located at the equator of the block sphere. For example, in this case, where the poles and zero, they overlap with each other, you can get a constant contrast on the entire sphere. But they can no longer overlap with each other, but meander on the entire on the equator, and this gives you still Abelian condition. They can also form second order Poisson zero, which is also still an Abelian version. But once the gauge potential are chosen to be non-Abelian, you find that the Poisson zero, they move away from the equator. These pairs and these pairs, and all of these predictions are confirmed with our experiment. So this measurement is actually done in the block sphere subspace, and we can do similar measurement in the torus subspace by fix the incident pseudospin, but change the synthetic gauge field theta and phi. And again, this time we find that we can indeed control the magnitude of the gauge field in different orientations. So I think what this could be exciting is that you're now, again, can use the similar rationale to put those non-Abelian gauge field components on a lattice. For example, to build a non-Abelian lattices and study the dynamics of the system. You can generalize the Hofstadter model with those non-Abelian gauge potentials. For example, you can decorate the links by putting the gauge potential on the same arm or on orthogonal arms, and this will give you a quite pronounced revision to the Hofstadter model. And you can find that when the system reduced to Abelian, for example, rightmost and leftmost, the system reduced to Abelian and spectrum reduced to the butterfly. But if they're not Abelian, you get very complex patterns, revised Hofstadter patterns. And we hope that this could give you a photonic realization of Z2 topological insulators, because I hope that this can be a robust realization, because it turns out many of the topological insulator realized in photonics actually fall into this fragile topology category. So we hope that this can be a relatively more robust realization. So I'd like to summarize my talk here. The first part is this nanoscale electromagnetism. It's verified from a far-field scattering measurement. We hope that the theoretical framework can inspire more unified and efficiency array down that's valid for length scale smaller than 1 nanometers. And we hope that the experiment can inspire measurement of the D parameters of other interface, eventually leads to a compilation of this handbook of optical constants of interface that's complementary to this Palette book that people use day to day. And I also hope that these measurements could also be helpful for various of nanoscale devices in both optics and electronics. So for the scattering from free electrons, we derive an upper limit to the spontaneous emission, and we show that slow electrons can be efficient in the near field, and transparent materials can be efficient than conductive one if you devise your structure wisely and couple them to a good resonance that can provide you enhancement as well as a radiative coupling. So for the third part, we observe the non-abelian AB effect with synthetic gauge fields. And we hope that these gauge fields can be useful for non-abelian lattice simulations with both fiber optics and integrated photonics such as lithium nanobates. So that's the end of my talk, and thank you very much for your attention.
Appreciate it. Question?